Greetings, everybody. Let's begin our discussion of trigonometric integrals. So kind of to start out, the problems that we'll be seeing in this section really come in a couple of different flavors. We'll be looking at either products of sines and cosines, or we'll be seeing products of secants and tangents. And so kind of variations on what kind of powers do we have on the sines and the cosines, what kind of powers do we have on the secants and the tangents, how can we use our trig identities and our derivative formulas to kind of utilize in each one of those situations to find the integrals that we need to. So let's begin by looking at one of the problems that kind of fit this. So suppose that somebody asks us to evaluate the integral of sine to the fifth times cosine squared. Okay, so what we're seeing here is, we've got a product of sines and cosines. And so good things to kind of keep in mind are our derivative formulas for our sine and cosine. So remember that we've got the derivative of sine just being cosine. We've got the derivative of cosine being minus sine, and something that may come in handy, our trig identity involving our sines and cosines, the one that everybody remembers, that if we've got sine squared of x plus cosine squared of x, then that gives us 1. And so kind of usually how we'll incorporate that is we'll just arrange one of those trig functions on either side. So we've either got our power of sine as 1 minus cosine squared, or we can write our power of cosine as 1 minus sine squared. And it's these formulas that, depending on what powers of sine and cosine that we're given, that we're going to leverage along with this trig identity to kind of solve our problems, to maybe end up transforming things into a U substitution. So let's tackle this problem and see exactly how we might do that. All right, so what we're given is a sine to the fifth power and a cosine squared. And so because we've got that sine to the fifth power, what that kind of gives us is something where we can take out an extra power of sine. We can take a power of sine to use as a du for a U substitution with cosine. Okay, now the thing that actually makes that happen is the fact that the power on the sine is odd. This is possible because the power on sine is odd. Okay, what that lets us do is to convert our remaining powers of sines into cosine using our trig identity. So let's actually see how that works. So let's take out a power of sine. So if we take out 1 power of sine, that leaves us sine to the 4th power. Then we've got our cosine squared, and then we've got our power of sine that we took out. So this part, eventually kind of looking forward, is going to become our du when we do our u substitution. But we're not quite there yet because we need to be able to convert these powers of sine into some kind of an expression involving cosine so that we can use our u substitution with u being cosine. And so the question is, how can we do that? Well, here's where the power of the sine being odd comes into play. So what we can do then is to say that our integral of sine to the 4th really becomes sine squared squared. And so that we've got cosine squared and then sine of x dx. So now using our trig identity, we can rewrite that sine squared as 1 minus cosine squared. So we've got 1 minus cosine squared squared, cosine squared of x, and then sine of x dx. So now what we have here is a single expression involving cosine. Okay, so we've got a single expression in cosine, and for u equal to cosine of x. And then we've got our du being derivative of cosine being minus sine of x. Let's clean that up just a little bit. So we've got our derivative du being minus sine of x dx. And so we've got here our minus du that we can use. We've got an expression involving u, and so what will happen then is this will just become a polynomial in u, which, okay, we know how to integrate polynomials, and that's awesome and easy, and so we've kind of conquered this problem. So let's go on the next step and write that out and see how that happens. So what we started with was sine to the 5th x cosine squared of x dx. We did our expressions, and we said this ended up being our 1 minus cosine squared squared. We had our cosine squared, and then we had our sine of x dx. And so if we did our u substitution, so u being cosine, du being minus sine of x dx, now our integral becomes the integral of 1 minus u squared squared times a u squared times a minus du. So the integral that we have to do now just looks like a negative integral 1 minus u squared squared times u squared du, which now we've got a polynomial in u, and that is easy to integrate. We know how to do that. We can just expand that, distribute our u squared, and go from there. So let's do exactly that. So what do we have? Minus our integral of, if we expand, we've got 1 minus 2u squared plus u to the 4th times our u squared du, which if we distribute, now we've got the integral of u squared minus 2u to the 4th plus u to the 6th du. And so this becomes, sure enough, something that's easy to do with our power rule. All right, so now to kind of bring us back to where we were, we started off with our integral of sine to the fifth times cosine squared. We did a u substitution on that one, which enabled us to transform this integral into this polynomial of minus the integral of u squared minus 2u to the fourth plus u to the sixth. And for that one, we can just use our power rule. So we've got our minus 1/3 u cubed plus our 2/5 u to the fifth minus a 1/7 u to the seventh plus our arbitrary constant. And so if we go back, then using our trig substitution with u being cosine, we get a final answer of minus 1/3 cosine cubed plus 2/5 cosine to the fifth of x minus a 1/7 cosine to the seventh of x plus our arbitrary constant. And so that kind of gets us where we want to go. And so at this point, once we've got this thing solved, it's not bad to go back and say, all right, what were the steps that really made that happen? And so kind of what was the important idea in doing this? And the thing that kind of hinged on making this procedure work is that we had an odd power of sine. And that odd power of sine then led us to, we could take out 1 power of sine. So we could hold 1 power of sine and convert the others using our trig identity to an expression involving only cosine. And so once we did that, so we can hold out 1 power of sine, convert the others to cosine using our trig identity, and that set us up for a u substitution with cosine to make a polynomial. And that was the key that really made it work. So we were recognizing this odd power of sine. We used our trig identities and our derivative formulas to kind of manipulate this into a situation where we could do a u sub with the power of cosine, so a u substitution with only cosine, and that would get us where we want to go. Now, pretty much any time that's the case, we're able to do exactly that. That if we happen to see an odd power of sine or we happen to see an odd power of cosine, it'll work. So let's kind of bring this home with another example to kind of illustrate that point one more time, that we've got now the integral of sine to the fifth and cosine to the seventh. And just to kind of show you that it would work in either case, we won't do this one all the way to completion, but we'll show you that because we've got 2 odd powers, you do have your choice. And so kind of the first thing we could say, all right, well, we've got an odd power of sine. So since we've got an odd power of sine, we could rewrite this to take out 1 power of sine. So we've got our sine to the fourth, and then our cosine to the seventh, and then we've got our extra power of sine that we took out, dx. And so that what would happen then in that case, well, kind of our next step would then be to say, all right, convert our powers of sine into cosine. And so we can do that by saying that this will be sine squared squared. So our sine to the fourth becomes sine squared squared, cosine to the seventh times the sine of x dx. And then using our trig identity, this thing becomes 1 minus cosine squared squared cosine to the seventh times sine of x dx, so that with a u substitution, with u being cosine, du being minus sine of x dx, this integral then becomes the integral of 1 minus u squared squared u to the seventh power times a minus du. And so with that substitution, now we've gone from our trigonometric integral into something that looks like a polynomial that we can expand and then evaluate. Expand and evaluate. Okay, then kind of by that same token, there wasn't really anything special about the sine that we chose, that we had an odd power on sine, and that's kind of what made it work. But we could also try power with the cosine. So if we've got the integral of sine to the fifth x cosine to the seventh of x dx, there's nothing really holding us back from saying, oh, I can take out this power of cosine. So if I did that, what would happen? So I've got my sine to the fifth, cosine to the sixth power times a cosine of x dx. And so now the cosine of x dx will become part of my du, with u being in the sine. And so what happens, I can convert by, since the power on cosine was odd, I take one power away. Now I've got an even power, and I can rewrite my remaining powers of cosine with my trig identity. So I've got sine to the fifth. Now I've got cosine squared cubed to give me a cosine to the sixth, and then I've got a cosine of x dx. So then I can convert with my trig identity. I've got my sine to the fifth, my 1 minus sine squared becomes my cosine squared. So I've got all of that raised to the third power, cosine of x dx. And again, with the u substitution now, with my u being sine, my du being cosine of x dx, my integral becomes the integral of u to the fifth, 1 minus u squared to the third power, and du. So again, I get a polynomial in u that I can just expand and integrate at that point, and I'm able to solve my integral. And so the thing that made this work in each one of these two cases is that I had odd powers. So the odd powers of sine and the odd powers of cosine really let me go either way. I could do a substitution with u, or I could do a substitution with cosine, or I could do a substitution with sine, because the odd powers then made that work. Take away one of my odd powers, I can then convert with my trig identity into the other trig function, so that my u substitution is going to work. And so hopefully This has kind of been insightful in one possible case that you can look for when you're integrating products of sines and cosine to powers, that if one of the powers happen to be odd, now you're set and you know what to do. So I hope you enjoyed this, and I will see you guys next time.